So what is here we kind of left off this yesterday. So we want to find all of the values of C guaranteed by the mean value theorem, right? Let's rehearse the mean value theorem though, right? It's an existence theorem. So if something is true, then it guarantees the existence of something. So what was it? For the function f, if what is true?
If it's smooth on the closed interval of a to b,
Yeah.
then there exists a number c such that f prime of c is f of b minus f of a over b minus a.
Okay, good. We can summarize.
I know what it is in English, I can tell you that.
Yeah.
I just,
So if a function is smooth on a closed interval, right, then that guarantees at least one value on the interior of the interval where the slope of the tangent line equals the slope of the secant line.
assuming that A
Right.
and C, A and B and C are the same value.
Assuming that what?
That
No,
A
that
and
was
C
Raleigh's
value.
theorem. That was Raleigh's theorem.
Oh.
Remember, mean value theorem is only tilted, right?
Oh.
And so we're just right.
Okay.
The slope of the tangent equals the slope of the
Slope of the secant line, because the slope of the secant line means that the slope of the line connecting the endpoints of the interval, right? That's secant line is a line that purposely intersects a function in two places, and you use it to find an average rate of change, right? Tangent is, you know what tangent is.
Is a straight line considered smooth?
A straight line is considered smooth, yeah, it is, but it's boring to deal with. But
Yeah.
you don't really need calculus to deal with a straight line,
What?
and so it's, yeah, I mean, really, you don't need
Yeah.
calculus to deal with that. So it's not. So that's one that we sidestep in calculus just because it's too easy.
So
You know,
would
we
that
need to
not
read it.
be included in the mean value theorem?
Oh, no, it is. Of course it is. Yeah.
But
so-
there's no, oh, yeah, I see how that, cause, yep,
Every point would work. Yeah.
Yeah.
Okay, so what's our derivative here?
3x squared plus 2.
Okay, so what do we do?
So you have to find the critical numbers. Or no, wait.
No,
Never mind.
not necessarily, right? We've got it now. We're going to set up the premise of the mean value theorem is that the slope of the secant line, right? So it's
Oh, it's
where
d equals square root
f prime of c equals the slope of the secant line. So if this is A and that's B, what is it in general? What's the secant line? What's the rise?
B minus A.
Or
f
f of B minus f of A over
b
run.
minus a.
B minus A. Yeah. Okay. So then, how's that going to look for us? So it's going to look like, well, we don't have to call these C. Let's just solve for X, and then the values we get we'll call C. So then this is just going to be 3x squared plus 2. And what's this going to be? What's f of B?
3.
Oh, that's B, sorry.
Three.
F of B.
3.
Yeah, 3, right? What's f of A?
1.
Positive.
Negative 3.
Positive.
No, negative 2 plus 2.
Oh, positive 2.
Negative 3.
Negative 3,
It's
right?
negative 3, but
Negative
minus, so it's positive.
Okay. Divided by
2A.
2A. It's always the answer, right? B
Wait,
minus A.
how'd
Two.
you
Because if I evaluate this at negative 1, I get negative 1 cubed plus 2 times negative 1, which is negative 3.
Oh, yeah.
Okay?
Did you just write it as 3 plus 3 plus top code?
Yeah.
Because we're obviously doing the minus thing.
So that just gives me 3.
Yeah.
Okay? So then I end up with I just got to solve the equation now. 3x squared plus 2 equals 3, right? So what do I get? What do I have to do to isolate x?
Minus 2.
Subtract 2.
Divided by 3.
Square root it.
So what do I have to do to that?
Multiply top bottom and square root.
Good. Plus or minus square root of 3 over 3 for my two values, right? But are those both guaranteed? Those both are guaranteed by the mean value theorem because they fall within, right, within our interval. Okay. Square root of 3 over 3 is less than 1, so negative that is going to be like negative 0 point something, right? And then positive 0 point something. Right?
So that's like the answer.
So those would be the two answers, I think. See, is that what they're asking? Yep, that's it. Right. What if our interval, just hypothetically, what if our interval, say everything was the same, but our interval went from 0 to 1? Then I couldn't keep both those, could I? Would go away, right? I could only keep the positive one. That's the only one guaranteed, because the mean value theorem only guarantees at least one value in the interval. So any values I find outside of the interval are not values guaranteed by the mean value theorem, and those would be, including those being correct.
So if you had the interval from 0 to 1, would the negative square root of 3 over 3 be considered extraneous? Or
Yeah,
just,
it'd be extra. It's it might be interesting in a different situation, but it's not. It doesn't pertain to the mean value theorem. Okay. So that's it. Mean value theorem stuff's pretty easy. Not a big deal. Let's look at maybe one application of that. How about something like, yes. There's one on here I really liked. Okay, how could we do number 61? Should think about that one a little bit. 61. Two bicyclists begin a race at 8 a.m. They both finish the race 2 hours and 15 minutes later. Prove that at some time during the race, the bicyclists are traveling at the same velocity.
By that logic, do they have to be traveling at the same velocity at the same time?
No.
Oh, okay. Can I just cite the mean value theorem as our answer?
Well, kind of. If you can show that the conditions are met, then you could.
Okay.
What's the one that gives?
Because they have to accelerate to some speed, wouldn't there logically have to be one, like a velocity at some point where that's the same? Like they both have to be accelerating at least 2 meters a second, or like 0.1 meters a second at some point, twice, at the very least,
So,
no matter what.
okay, so how does the mean value theorem apply there? So we're looking at,
well,
they both, okay, have this at the same velocity. So what quantities are we really comparing here? Now, normally we're thinking about, like if we look at our last example, I want you to see one thing here. So we've got functions, f of x, right? In the mean value theorem, it guarantees that at some point the slopes of these functions, right, the instantaneous rate of change, meaning the slope of the tangent line is going to equal the slope of the secant line. Okay, so for this problem, instead of f of x, what have we got? Yeah, and what function would that be? What kind of function is it going to be? Is it a velocity function?
Isn't it the slope of an acceleration function as well?
It's the, okay, so velocity is the derivative of what?
Distance.
Position, right? Velocity is the derivative of a position. So really these are position functions, right? So we wanna just, so let's just take bicyclist number 1, right? If bicyclist number 1 starts the race at 8 AM and he finishes at 10:15, and okay, that's kind of a weird question. Because, okay, that's not really the one I want, because it doesn't apply as directly. Let's change this question very slightly. Let's say that they finish at the same place in the same time. Okay?
That's not implied,
Well, I didn't know if, I guess.
like finish lines.
Finish
Okay,
lines
yeah,
don't
okay, I guess it is. Yeah, I guess it is implied. Otherwise, it's kind of a weird question. So I guess it exists, the finish line, okay. So then, let's just take bicyclist number 1. His position function is, he starts at 0 position and he ends at however long the race is, right? Does that make sense? Let's just say the race is, I don't know, how long is, let's just say it to make it convenient, he'd really be going fast, but let's say that it is 67.5 miles, okay? Okay, so what's his average? What's the slope of the secant line? What's his average rate of change of position, meaning average velocity?
It's like 60 over.
67.5 divided by 2.25, right? So it'd be 30. So 30 miles per hour. You with me on that? So that's his average speed. Is the position function, here's the part we want to get at, is the position function smooth? And why?
Because you can't,
Because you don't,
you don't, there's no acceleration or
If you-
deceleration.
if your pen doesn't leave the ground, if you would like draw like the track, it wouldn't leave the ground. Because
But it's smooth
And-
because,
And it couldn't, could it? I mean, for me to draw, think about that now, if I'm gonna draw the position function for this thing. So. Say they're traveling in a line, so let's just call it X. Right, there's no way that I could start off with a position of 0 and end up here at a position of whatever, however far you said he went, 67.5 miles, right? There's no way I could ever do something that would make this anything other than smooth, right? What does smooth mean? Continuous. Well, obviously, this can't happen, right? Unless he's microscopically small bicyclist and some quantum effects are taken over, right? That can't happen. You can't just instantaneously move from point A to point B,
Yeah.
right? Okay, that can't happen. What's the other thing here for it to be smooth? It has to be differentiable, right? So the other thing then that couldn't happen is this. We couldn't go, we can't have anything like that. How come?
because they can't change speed or velocity like that instantly.
Yeah.
It's impossible.
That velocity can't change instantly, right? That can't happen. We know, just from our everyday experience, we know it can't happen, but physics forbids it. That would require an infinite acceleration, right? Which would require infinite force, which would be, it couldn't have, if it did happen, you would be spaghettified, and people don't do that when they're riding bikes. They don't just turn into goo all of a sudden, that's, right? So we know that because of our experience, the velocity can only change smoothly, right? Even if big accelerations feel different than small accelerations, but you can't have infinite acceleration.
Could you do that on if it was speed only?
If it was, you could. Their velocity graph could do this, right? Because the velocity would be changing. Does that make sense? Okay, but you just can't do it with a position graph. Okay, because then you're going from an instantaneous this velocity to that velocity, which can't happen. Right, that never happens in life. So then, just because of the fact that this is a physical situation like that, it is a smooth function. And so, regardless of the specific strategies, the race strategies that they both use when they're going fast and when they're going slow, if they start at the same place and end at the same place at the same time, that means they both have the same average velocity, right? And by the mean value theorem, at least once during the race, they must have traveled at that velocity, right? And so therefore, at some point during the race, they may be at different times, but they must have traveled the same speed at least once, even though they may have been doing it at different times. Does that make sense? Okay. All right, so next issue. I want to just introduce you to something. I have a feeling I'm not going to be here later this week, so I don't want to lose out on any chance to talk about cool stuff. So let's talk about this. Let's talk about our search for relative extrema. Okay, let's take an example. I want you guys to come up with a strategy. And you will. You'll come up with a good strategy. So let's take an example like, how about that'd be a good one. Yeah, I like this guy. Let's do this one. Okay, so the first question I'm going to ask you, and later on, I'm going to give you the same thing. I'm going to come back and say, what if I'd asked you this? And you'll be able to tell me the answer based on what we do. First question is, or the first task, is find all relative extrema. So how are we going to do that? Where do relative extrema always have to live?
The tangent is zero.
Or at critical numbers, right? Okay, so we've got to find the critical numbers. So what's the first step then?
Derivative.
Yeah, we got to differentiate. So f prime of x is what? Okay, so let's find our critical numbers.
Could you just change the equation to x squared minus x?
Well, we can't, okay. Yes and no. We don't want to change this equation because the derivative is 3x squared minus 3x, right? But what we could say is kind of the stuff like we talked about yesterday. We could say, okay, where is f prime equal to 0? So f prime equals 0 when 3x squared minus 3x equals 0, which is the same thing as x squared minus x equals 0, right? See the difference? We haven't changed what the derivative is. We've just said that the solution to this equation is the same as the solution to that equation, right? And so how are we going to solve that?
Split it into two equations.
Okay, so meaning,
Like at x minus 1 equals 0, and then.
okay, so we're going to
take out
factor
x.
it.
Yeah.
We're going to factor it. So we'll factor out an x and then find the solutions, right? So we're going to end up with the solutions x equals 0 or x equals 1. Let's build our table. Did I specify a domain? I didn't. So what's the presumed domain of this then? It's going to be its natural domain, which means the biggest domain that we can find that applies to that function, which is what? all reals. There's no reason, there's nothing in our function that's ever gonna throw up a red flag, right? So then the first thing we're gonna do down here is we're gonna do this. To indicate that the domain is all reals. Okay, what numbers were important to us on that domain?
0 and 1.
0 and 1. 0 and 1 were big. 0 and 1, because what happened there?
That y prime equals 0.
Yeah, y prime equaled 0. And I guess something else I should have done, we never really looked for it, but is our first derivative going to be undefined anywhere? No. So we don't even really have any other type of critical numbers, right? There's all we have to look for are just the places where the derivative is 0. Does that make sense? Okay. Okay, so now those might or might not be critical numbers. How are we going to test? What could we do? Well, we could plug them in and we could find y values, couldn't we? Is that your suggestion? Okay, so we could do that. We could plug them in and find y values. And so if we do that, what do we get? So let's see, we're going to get f of 0 is 0, right? And f of 1 is
No, it's
negative 1/2. How am I going to know if those are peaks or valleys?
You could just plug in numbers next to them, or is that
Okay,
inefficient?
I could plug in numbers next to them, right? I could plug in test points on each of those intervals. How many test points am I going to have to choose? 3.
Arguably,
Why?
like for each one, because if you have this one, then if you have one to the each side, arguably only one.
Okay, where? Pick it.
2.
Okay, let's pick the test point 2.
Can you have test points at like fractions, like? you know,
Sure.
one?
Yeah, it can be anywhere, yeah. Okay, so at 2, what are we going to get back?
2 cubed.
And now, and what are you plugging these into? The 2 into? Into f of x, you're saying. Okay, that's fine. So if I plug it into f of x, f of 2 is going to be 8 minus 3/2 times 4 is going to be 8 minus 6.
Yeah.
So 2, okay? That's not quite enough though. I need more, don't I?
0.5.
Right, I'm gonna need other test points. So I could do like -1 and 0.5, those are both good, right? You can try -1 and 1/2. Okay, and what about at -1, what are we gonna get? -1/2? Oh, no,
No, it'd be
No, it's -1 minus 3/2, so.
yeah, so what's that gonna be? So
5/2?
-5/2. And at 1/2, yikes, 1/8 minus 3/8, is that right? So -1/4,
Mental math.
right? Everybody buy that?
I'm trusting your degree.
Yeah.
Okay. So now that's enough, isn't it? Isn't that enough? Because let's look at these y values. This y value is going to be greater than that one, and this y value is greater than that one. So what is it?
Low.
It's going to be the low point of those 3, so it's a minimum, isn't it? Right? This one is less than 0, and this one is less than 0, so this is the high point of those 3 points, and so it has to be a maximum, right? Does that make sense?
And so the 0 is
Oh,
just,
I see.
wait, what's?
And
I
so-
get it.
So we know then if we were to sketch this, and this is where we're going with this, we want to be able to create a sketch of this, then we just know it's got to look like, so it's got to look like this. I've got a point there and a point at 1, -1/2, so I've got a point there, and it's got to do something like this. Right? Locally. That's all we know for this point.
So wouldn't the 0 be the negative? Wait,
No, 0's positive, because 0's bigger than those values.
yeah, so it would be the high, or what?
yes.
Right, so it's the high, right? Okay, that's not bad. There's a better way though. There's a better way. And this is something, take notes on this, because this is something that I have a real passion for, this tabular form of this stuff. And so I've got some rules for you that work. I've never seen them, but I know they work. I proved it for myself. I know these work. So you want to work. You want to work as far down the table as you can. As a general rule. It makes life easier. I'll show you how. So let's work down in the y prime. Instead of using these test points, evaluating them at the function, let's not bother with that. Unless we'll never need to. Never need to. Let's work down here in the third row. So let's evaluate the first derivative
if
at
it's
2.
positive and then if it's negative.
Aha. And we don't even have to, here's the advantage. We don't even have to be specific. We just have to know the sign of the derivative. That's it, whether it's positive, negative, or 0. Okay? So if I evaluate the derivative at 2, I'm going to get 3 times 4 minus 3 times 2. Everybody agree that's positive? I don't even have to think about what the exact value is. It's positive, right? So I can put a plus sign there. Okay? What about at 1/2? 1/2 squared is smaller than 1/2. So that's going to be negative, isn't it?
Yep.
Right? Using whatever logic you want to. And you can figure out the value, but you don't often need to. What about at -1? Well, that's going to give me positive plus positive. That's definitely positive. Both terms are positive, right? Okay, what does that tell me? Now think about the shape of this thing. What does a positive derivative mean? What's-
Slope positive slope.
Okay, so what do you suppose we would call that? That's a what kind of function from left to right? It's an increasing function. Yeah. So on this interval, the function is increasing, right? On the interval from 0 to 1, the derivative is negative, which is what kind of function? Decreasing. And the interval from 1 up, it's increasing again. That's all we need to know, isn't it? What's the definition of the transition point from an increasing to a decreasing function? That's a peak, isn't it? Right? What's the definition of the transition from a decreasing to an increasing function? Well, that's a valley, right? So we know that's, in mathematical terms, that's a relative max and that's a relative min. Plus, it also emphasizes the intervals on which the function is increasing and decreasing, which is important to know. Because I could have also asked this question in the form I might have said, instead I might have said something like, find all increasing and decreasing intervals. Right? So how would we have done that then? Let's go back and look at our result. We could have said f
Is it increasing or decreasing from negative to 0?
from
The 1/2.
right here?
Yeah.
Decreasing.
From negative to 0?
From
So from
0 to 1, it's decreasing because the test value, the test point gave us a
so
negative.
it's from-
Right, does that make sense? So then if we want to write these intervals, we could say f is increasing on what interval? Let's use interval notation.
Negative infinity to 0.
Right, which, another way of saying that, just x is less than 0. And,
1.
oh, sorry, not and, that's the wrong term. It drives me nuts when people use and or interchangeably, and I just did, because they're not. You can't be both at the same time, so it's or, that just means or.
Well, it can be and or, can't it?
No,
No?
because how could an ant be on this interval and that interval simultaneously? You can't.
Doesn't it
Right.
have to be like a U shape?
It's a V,
Oh, it's a V.
is the logical and. Sometimes you can use the union symbol too, which looks
Yeah.
like that.
That's what we did
Yeah, I've
in
seen that in
Jones.
trig.
And that's fine, either one would be fine.
Okay.
This is kind of an algebra symbol and that's kind of a logical symbol. They both would work.
Okay.
Yeah. Whichever one, doesn't matter. Or you can even use a comma. Comma implies an or also, if you put a comma in between those intervals. So any of those three technically would work. And then what's the other one? 1 to infinity, right? Okay, we could say the function is decreasing on what interval? 0 to 1, okay? That's an and, isn't it? Because x is greater than 0 and less than 1, right? Those conditions both must be met to be on that interval.
So would you include the 0, 1, or would you exclude? So would you use brackets or parentheses?
No, okay, good question. So is the function, let's look at our picture. Is the function increasing or decreasing there? No. So you'd have to use parentheses, right? It's an open interval. And it's not decreasing, increasing or decreasing there either, right? It's the transition point. So it's only the interior intervals where it's going to be increasing or decreasing. Okay. By the way, that is what we call in calculus the first derivative test. Okay.
So that was a test.
We have a test over this.
Will we have a test over the first derivative test? Yes, we will. Yeah.
Wait, so the first derivative test is which part?
It is using the table. Well, I mean, it is checking a test value for the derivative between critical numbers. Okay. Using the table that way though is something I want you to get some practice with. All right, that's good stuff.